100,000 charge cycles. Sounds immortal, right? But if that number were real under EV conditions, why does not any electric car come with a 50-year battery warranty? If a battery can truly survive that many cycles, what does it look like inside after tens of thousands of charge-discharge events? And more importantly, is that figure based on real driving or laboratory perfection? Solid-state batteries replace flammable liquid electrolytes with solid ceramic, sulfide, or polymer electrolytes. That change alone reshapes the entire degradation pathway. Most advanced solid-state concepts also use lithium metal anodes instead of graphite. Lithium metal delivers a theoretical specific capacity of 3,860 mAh per gram, more than 10 times higher than graphite's 372 mAh per gram. This is why projected energy densities often reach 400 to 500 watt-hours per kilogram at the cell level, compared to 250 to 300 watt-hours per kilogram for today's mainstream EV lithium-ion packs. Higher energy density is real, but cycle life is the battlefield. In laboratory environments, certain sulfide-based solid electrolytes with ionic conductivity above 10 to the power of -3 Siemens per centimeter, comparable to liquid electrolytes, have demonstrated impressive durability. Some prototypes exceed 10,000 cycles under shallow depth of discharge conditions. A few experimental setups even approach 20,000 cycles, under tightly constrained microcycling windows with minimal strain. Theoretical projections can stretch toward 100,000 cycles. But here is the key question. Are those full automotive cycles? Consider a Tesla Model 3 with roughly 75 kilowatt-hours usable capacity and around 400 to 500 kilometers of range. One full cycle equals hundreds of kilometers of driving. Even 3,000 full cycles would translate to well over 1 million kilometers. Current high-quality LFP packs in EVs already reach 4,000 to 6,000 cycles to 80% capacity under moderate usage. That is more than most vehicles will ever need. So if someone claims 100,000 cycles for a solid-state design, we must immediately ask full depth, partial depth, at what temperature, at what C rate? Inside a lithium metal solid-state cell, every charge involves lithium plating onto the anode, and every discharge strips it away. Unlike graphite, which stores lithium between stable carbon layers, lithium metal physically deposits and dissolves. That repeated plating and stripping causes volume change. Even tiny irregularities in deposition can create uneven surfaces over thousands of cycles. These irregularities amplify. Solid electrolytes suppress dendrite penetration better than liquid electrolytes. That is a major safety advantage. However, they introduce mechanical constraints. Ceramic and sulfide electrolytes are rigid and sometimes brittle. During repeated cycling, stress accumulates at the lithium electrolyte interface. Voids can form when lithium strips unevenly. Those voids increase local current density and raise interfacial resistance. Many experimental solid-state cells require stack pressures between 5 and 30 megapascals to maintain stable contact at the interface. Maintaining that pressure consistently inside an EV pack over years of vibration, temperature swings, and mechanical shock is a serious engineering challenge. Now, scale that stress over 10,000 full cycles. Even with optimized materials, impedance tends to rise. And power capability matters just as much as capacity in an electric vehicle. If internal resistance doubles, acceleration weakens and fast charging slows, even if nominal capacity remains high. Fast charging exposes another layer of stress. Modern EVs, such as the Hyundai Ioniq 5 and Porsche Taycan, operate at 200 to 350 kilowatts peak charging power. High current density increases lithium flux dramatically. In liquid cells, this risks lithium plating. In solid-state systems, it can produce localized stress concentrations and microfractures in brittle electrolytes. Repeating that stress thousands of times compounds mechanical fatigue. Temperature fluctuations make the situation more complex. EV batteries routinely operate between near-freezing winter conditions and above 45 degrees Celsius during summer fast charging. Solid electrolytes and cathode materials expand at different rates. Thermal mismatch creates additional mechanical strain at interfaces. Over thousands of cycles, thermal fatigue adds to electrochemical fatigue. Now let us quantify what 100,000 full cycles would require from a degradation perspective. To retain 80% capacity after 100,000 full depth cycles, average per cycle capacity loss must stay below approximately 0.0002%. For comparison, many high-performance lithium-ion EV cells today degrade on the order of 0.02% to 0.05% per full cycle under real-world conditions. Achieving a 100-fold reduction in per-cycle degradation under full automotive stress would represent a historic leap in materials science. That does not mean solid-state batteries cannot dramatically improve longevity. Eliminating flammable liquid electrolyte improves safety margins. Lithium metal increases energy density. Some solid electrolytes exhibit strong chemical stability against high-voltage cathodes. Realistically, solid-state technology could double or even triple cycle life compared to certain high-nickel lithium-ion chemistries, and that alone would be transformative. Consider a robotaxi fleet cycling twice per day. Over 10 years, that vehicle might accumulate roughly 7,000 full cycles. A solid-state battery capable of 15,000 full cycles with strong capacity retention would comfortably exceed that demand. For grid-connected storage cycling daily, 10,000 to 20,000 cycles would already support decades of service. In that context, the practical revolution is not 100,000 cycles, it is stable, high power, 10,000 plus full cycles under realistic temperature and charging conditions. So what does 100,000 cycles most likely represent? It typically implies shallow cycling in laboratory environments, perhaps 10% depth of discharge, controlled temperature near 25 degrees Celsius, and moderate current density. In that narrow window, mechanical strain per cycle is small. Total lithium movement per cycle is limited. Degradation slows dramatically. Under those specific parameters, cycle counts can skyrocket. But that scenario is not equivalent to an EV accelerating onto a highway, fast charging at 250 kilowatts, and operating across seasonal extremes. Inside any battery, solid state included, lithium ions move, materials expand and contract, interfaces age, and stress accumulates. Solid-state designs shift degradation from liquid electrolyte decomposition toward interfacial mechanical fatigue and contact instability. They reduce fire risk and may significantly extend useful life.